Hi everybody, this is Matt Ingram again with the replication of Ballard et al. This is now replication 1C. In A we used Geoda, in B we used R, and now we are using the spatial analysis library in Python. The Python programming languages, and then this one library, PySal. So as before, I assume you have downloaded and installed the required software environment, so that means downloading Python and the Python spatial analysis library. As I noted in the separate tour video, you could do this multiple ways. I demonstrated two different ways in which you could do this. So I assume that you have the software and the library downloaded and installed on your machine. I also assume that you've downloaded all of the necessary data from Blackboard, which at this stage in the course everybody has, since we've been talking about the replication in class already for several weeks. And lastly, as before, these replication steps should be familiar to you by now. We're going to replicate maps 1 through 4, the LISA cluster maps, then set up the basic OLS regression, do some diagnostics, and then conduct the two main spatial econometric analyses, or the spatial regressions, the lag version of the regression and the error version of the regression. So let's turn now to Python. In the options that I mentioned for downloading Python, I said that I downloaded Anaconda. The way I access that is through my start menu. If I go to Programs, here is Anaconda. There's various ways that you could access Python through the command shell, through IPython, or through the Spider editor. The editor is my preferred version. This is essentially the equivalent to an R script or a stata do file, and this is what it looks like when you open the Spider editor. If you like the RStudio environment, this is very familiar. This is also much like the stata interface. So you have your coding or your syntax or your editing space over here on the left, and then your results window is down here on the bottom right. You have several options, as you do in RStudio. You have like a history of all your commands that you can access. You can see everything that I've been doing recently here in my history log. But this is basically your results window. You can see that I'm using Python 2.7 and Anaconda 2.1 and some other startup information here. And here we have another window where we can inspect different objects that are loaded in, inspect variables, and inspect different files. I'll leave it on the Variable Explorer. This is our basic setup in the Spider editor. Up at the top you can also see which version of Python I am running. And then you can load and save different files as you're editing. Again, if you're familiar with stata, this is very much like a do file environment. If you're familiar with R, this is essentially your R script, and this interface is very much like RStudio. So up at the top I've included some basic information about when I created this, when I last updated this. By this time, again, I assume that you've downloaded and installed Python. I'm just scrolling down here. As I've done before with R, I try to provide some helpful commands here. So if you have a command that you don't quite understand how it works, you can type help, open parentheses, quote, the command, close quote, close parentheses. Directory will also give you a list of options for a particular object. This is not the directory for your working directory, for your file directory. This is a directory for the objects that you're manipulating within the program. So for instance, if you build a database out of using a command, so you create an object that's a table or a matrix or a vector, you can then generate, or for instance, if you generate regression results, and so now you've got this object that contains all these regression results. If you use a directory command, you can see all of the different options that you can execute on that object that contains the regression results. If you want to set aside a line for a comment, that is, it's not going to be executed, use the pound sign. This is very much like R. If you want to set aside a whole area for comments, you can just start that comment area with a triple quote, type out your comments without needing to type the pound sign, and then close that comment section with another series of triple quotes. And then if you have a long series of comments and of commands that are going to go overlapping many lines, you can use the backslash. You can use the backslash at the end of one line and then indent the next line, and so on, and keep indenting line by line, adding the backslash. And the command will read that as one full line, even though it's broken up across several lines. Alright, so that's it for some basic helpful commands. Now we get into working with the data. So the first thing you need to do is to check that you've loaded, well, to load the PySal package and to check the version. So if we highlight this command here, and then you want to hit Control Enter in Python, or in the Spider editor at least, not Control D as you might in Stata, or Control R as you might in R. So Control Enter, and you'll see over here on the right on the results window, I imported PySal with no errors. I can then check the PySal version. And you see here that I've got version 1.91, and then I've got some notes here about how often PySal is released. It's released every January and July on a semester basis. So now in March of 2015 we're using the January 2015 release. If you run this command PySal OpenCheck, it's just a quick diagnostic to make sure PySal loaded correctly. What you should see is this series of different file extensions. If you see this, then it's loaded correctly. You can ignore this import folium. This is just another library or package that is good for visualizations, but we'll come back to it later. And as we've done before, we always want to make sure that we're working within our within the right directory, and for that we need this OS package. So let's just import both of these. We can highlight everything and hit Control Enter, and if you then do os.get current working directory, so it's accessing your working directory, and here's where we are currently in Python scripts. We could list the contents of the directory using this material, but basically we first want to change the directory. So I've been using Python for these first two replications that we've been doing, but let's go to replication 1. Here's Baller et al. So let's go to that working directory. And just a reminder that that's my working directory, not necessarily your working directory, so make sure that this file path in here is your working directory. You can see that it executed here just fine. Now we could just confirm that quickly, get working directory, it is the same, and we could check what files are in there, say, and we can see all the different files that are in this replication directly. So now let's just check to see, one way you could check to see is if your shapefile is accessible is using this command os path exists. It's basically a query to see whether a file path exists, and it'll return this boolean true or false. So if the file path exists, it's true. If Python doesn't recognize the file path, then it'll tell you false. And then one last warning here, just to keep in mind that if you type directory with nothing in there, it's not going to access an object. It's just going to access the fundamental, the base Python directory for all of the, you could say pre-installed or elemental or basic functions within Python. So this is not the same as checking your current working directory. These two commands are not the same. For instance, we can just double check what our current directory is, but that is not the same as the Python base directory, right? That's the contents of it there. Alright, so we're in our right directory. We have checked that the file path exists to the right shapefile, to our national shapefile from Baller et al. Now let's just make sure we load a few of the other essential packages that we need. We've already done this, but let's just load again PySal. We can load it as anything we want. We could call it anything we want. So if we want to abbreviate it as PS, we could do that. NumPy, I forget what the NUM stands for, but it's basically numbers Python or numeric Python, is a wide range of numeric or mathematical or functions, and we'd like to have that as part of our basic setup. And then we have some other statistical functions that we'd like to have installed. So let's just import all of this. You can see that it imports quickly. It doesn't need to access any mirror or cite as R needs to do. But we've imported all of this as long as we've installed it previously. So we could do several things here. We could load the data into a data object. So we're going to call this object db, and then we're going to use this command pysal open to open the dbf portion of the shapefile, and we want to read it. Since we loaded pysal with the abbreviation ps up here, we could just use ps open. This national database from Baller et al. Is so commonly used these days that it's also part of the PySal package of examples, so you could also load it that way. This is the Messner et al. Data, and you also could specify the full file path as well, right? But since we already have set the current working directory, we don't have to use the full file path. But if you didn't want to bother with setting the working directory, you could just use the full file path if you wanted to. So let's just use one of these here for the national file, or national database of Baller et al. We'll load that. So that opened the national file and called it db. We could look at the length of db. This is just going to give us the dimensions. So it's 3085 observations long. That's correct, right? And then we could look at the header of db. This is going to give us a list of all of the variable names, basically the column headers. And there we are, right? The name, the state FIPS code, etc., and then all of our variables. Homicide rate 1960. This should all look familiar to you. We could extract then each individual variable using this format. So we could call the variable HR60. We could call this anything. Is going to take the object we've called db, examine it by column, and extract the column that's titled HR60, right? So it's going to basically grab this column over here. So if we execute that, if we execute that, Control Enter, you'll see no errors, and if we print that, you'll see it'll print all of the values in that column. In order to use with the spatial regression functions, we'd have to convert what is this list object that we've created. It's basically just a list of values, and we want to turn it into a vector. So we can use this function from NumPy and call it that. We can then check the shape of it, and you'll see now that it has 3085 rows in one column. That's the structure that we want, right? We want a vector that has the dimensions 3085 by 1. Again, that's rows first, column second. So one shortcut for doing all of this for setting this variable y is highlighted here. You could call this variable, this y name HR60, and then say y sorry, instead of reshaping it here, you could use this dot t at the end of the np array to transpose it. To transpose it. So you load it at the same time that you transpose it. Or you could use the same command for all of the independent variables: resource deprivation, population structure, median age, divorce rate, unemployment, and south. You could load them all at the same time and transpose them. You can also stack them all together. So you could do a horizontal stack of all of those variables. Or you could create this object with these string names and then use this command to collapse everything together. So if we just do this all at once, Control Enter, you'll see that it created a matrix that has 3085 rows and 6 columns. That is, all at once it created 6 columns with these titles. Right? So it extracted all of the columns from our DB object with those titles and created another matrix with those variables in column form. Very nice. Everything that I have just said, from importing PyCell all the way to creating the matrix of x vectors, could be collapsed into 6 lines here: importing PyCell, importing NumPy, loading the database, extracting and transposing y all at once, giving Python the name of all of your independent variables, and then extracting and transposing all of those independent variables into a single X matrix. So we could just run all of this at once, and it would execute, as you see over here, no errors. Now we've now loaded our database, we've extracted the dependent variable for 1960, and we've extracted all of the independent variables for 1960. So then the next step we construct spatial weights. I'm just going to take one brief pause here. So I'm going to complete this video here, having loaded the database and extracted the key variables. And in the next video, we'll construct the spatial weights. Thank you.